so this is the after introduce RSA, so we can start to outline the Shor's algorithm. Yeah, so I like to use one page to summarize this fact, so it's just concise. Okay, so idea is that the idea of Shor's algorithm is that your starting point is that somebody gives you a large integer equals to pq, where pq or just some odd prime. Okay, so the idea is that you hope somebody gives you a large n and you can find pq. Okay. So this algorithm contains the main contains many 3 steps, and only this part is quantum, and these 2 parts are classical. So quantum only contains a very small part, but the very crucial step. So the first is that you choose an integer which is larger than greater or equal to 1 or less or equal to n minus 1. Okay, so and then you compute the greatest common divisor x and n. Okay, so there will be 2 choices. The first case is that the greatest common divisor for x and n is not 1. So if this is the case, that you are very lucky that you just guess in p and q. But this is very you only have a very amount of possibilities, because if n is very large, then the x can only be choose p or q. Okay, so this possibility has only 1 over n. So if n is like 10 digits, then you have 1 over 10 to the 10. So this is very lucky. So in general, you will get GCD x n is which is 1. So if you like algebra, basically x belongs to the z, and the inverse, the multiplicative group of modulo n. Okay. Then idea is that if you apply Shor's algorithm, we will discuss in maybe next videos. The idea is that you can apply the quantum Shor's algorithm, basic quantum algorithm, to get such number s, which we assume that s contains 2 properties. The first property is s is even. So s is even is the first property. Also, s such that x to the power s divided by n, the remainder is 1. So s is equal to 1 mod n. So we can write this equation into this: s to the s power s divided by 2 minus 1 times s divided by 2 plus 1 equals 0 mod n. And we will further assume that neither x divided by 2 minus 1 nor not the s divided by 2 plus 1 is not a multiple of n. So basically, we assume that we have 2 conditions. One is that the s are even, one is that both are not multiple of n. Then if this is correct, then we can compute the greatest common divisor of this one and n, right? Because now the idea is that since this is not multiple of n, so this greatest common divisor must pick up some non-trivial factor, right? Because now this guy is not 0. Yeah, also this guy is not n, some multiple of n, right? So that means you will always catch up some non-trivial factor. So you can compute this guy, and you can get p and q. Okay, so this is the idea of Shor's algorithm. Okay, so the non-trivial part is how to get s. Okay, and this is called the period finding problem. Period finding. So actually, the Shor's algorithm is basically one kind of period finding. Okay. Okay, so let's talk about a little bit introduction to the how to find this period. Okay, so now idea is that let's talk about general setting of the period finding. Okay, so let's talk about general period finding. So idea is that if you have an function from, let's say, n to n, okay, such that you already guarantee that f of x equals fx plus l for some l larger than 0, which l is an integer. So you assume that l has some this f has some positive period l. So this is what you promise. So the idea is that you need to find l. Okay, but what the hell is related to our problem, right? So we know some algebra. We know that since x, suppose x to be the multiplicative group with modulo n, and this is abelian, right? So and this is finite group. Right, so we know that from Euler-Torsion's theorem. If you don't know that, you can go to my video channel and check the proof. So we know that x to the torsion phi of n equals to 1 must equal to 1 mod n. So that means there always exists some r such that xr to the 1 mod n. Right, because we know that eventually will go to 1 mod n. So that means it has a period, it has some r, which is integer such as x to the power r equals 1 mod n. Okay, so which tell you. So if you define f of n to be x to the power n mod n, then fn is periodic with period r. Okay. The reason is that f of n plus r is x to the power n plus r 1 mod n. X to n, x to r. So this is 1. X to r mod n. So I can choose r to be the smallest. So there exists the smallest positive r such that the x to r equal to 1 mod n. Okay, so the Shor's algorithm, the key idea for next video is that we need to find these. We need to create a quantum algorithm to find these fn. Okay, so let's quickly go through the idea we will start on the next video. So just as the original quantum algorithm, right? So first if the n, right, if we want to crack this n, then I can choose small n, which is 2 to n larger than n. Then I create all the so-called superposition, right? So this is the standard. This is the standard. Maybe each quantum algorithm starting with this step, right? I first create this, and I apply some UF, and I can design a UF on x will be x, and there's a register. Right, there's a register that I can get the x and let's say f of x, and the f of x. Why I define f of x is to be, let's say, I should say. Sorry, I used too many x as my notation, so it's not good. Let's say I use n. Okay. Okay. So sorry, n is also not good. So let's maybe I use I. Okay. So and you may have some like NCL or something, but I hope you add I, then you will be I like tensor with some register. So this is f of I, right? So f of I encoding this function. So f of I will be x to the I mod n. Right. So you will have this. Okay. So now you have a very good starting point. And the idea is that if you measure this, right? If you measure this guy, then we know that f of I is a periodic function of R. Right, so let's say we have f0, f1, f2, up to some points. Let's say fr. So fr is the same as f0, right? So it will stop. So after you measure fi, then you will get the following. You will get something like. Something like maybe you start from k, right? Then you will get some k plus let's say PR in the k plus 2r up to k plus r minus k plus something, let's say L, so L minus 1 R divided by square root of L, right? So this is the possible case that you may get. So this means that you get something because suppose you get k, right? You may get f of k at the f of k plus r, f of k plus 2r, because all of these f have the same value, and then you measure this, so the rest will be k. The rest of this first register will be k plus r, k plus 2r, k plus l minus 1r. Suppose there are l of them, square root of l, right? So this is your remaining state. So the idea is that how to extract r from this state. Okay, if one can extract this r, then we are done, right? So this is why we use a quantum Fourier transform. So this is the next the next video's results. Basically, next video tutorial I will introduce the quantum Fourier transform, and the quantum Fourier transform can have some magic power to extract some relations about this R, some information of this R, and we will see how this can help. So the Shor's algorithm is so amazing that it can solve. I mean, if you do not like quantum computing, but you like math, just like me, so it's very amazing that this type of period finding problem looks stupid. Like you just have some function and it has some period, but it's amazing that quantum computing can find some way to estimate this period, right? And without using it's very amazing that if you're classical, then somehow you need to start from f0 and start from f1 and start from f2, and then just to see which one is L, right? So, but for quantum computing, there is a shortcut called quantum Fourier transformation, and such one operations can give you the many applications. So maybe in the rest of in other videos, I can talk about there are many other applications of finding this guy. So we can talk about like Pell's equation or the hidden subgroup problem. So there are so many interesting results related to this quantum Fourier transformation and period finding. Okay, I will see you guys in the next videos. Be sure to subscribe to my channel. Thanks.